to a very special robotics seminar. It's a very special seminar because we have today a distinguished guest. He is what I think we can call a true pioneer in research. He started his career as a postdoc at the University of Toronto, where he developed a little thing called a convolutional net. You may have heard of that? Right? Yes? Okay. And then he went on to Bell Labs, where he did further development in neural networks, and then NEC, and finally professor at NYU, and now director of the AI research lab at Facebook. And certainly, a lot of the things that we use today in deep learning can be traced to his research as far back as over 30 years ago. So we are very happy to have Yann LeCun, yes, LeCun, not LeCun, here today. And yeah.
Thank you. Thank you, Martial. And it's Martial, not Marshall. Yeah, it's always a pleasure to come to CMU. The second time I ever came to the US, and I came to CMU. This was a little bit over 30 years ago, which I'm kind of embarrassed to admit. And it was the first Connectionist summer school organized by Jeff Hinton and Terry Sinofsky. And you can see a young Jeff Hinton here. He was a professor here, associate professor here at CMU. Terry Sinofsky, Jay McClelland, who used to be at CMU, Dave Tureski, who is still around. This is Michael Jordan. Jordan Pollack. There's a whole bunch of people here who are kind of, you know, went on to do great things. And that's me right there. I almost have as much hair, which is good. And this was a wonderful time for me. This was the first time, this was the first time that people started hearing about backprop. So backprop was the really hot thing at that time. The papers hadn't appeared yet. This was July 1986. The paper only came out, the book chapters from the PDP book kind of came out later, and the paper in Nature came out the year later. I already had been working on backprop at the time, some version of backprop on my own that kind of came up with independently. And so I hit it off directly with Jeff and various other people, which is how I kind of landed in Toronto the year after that when Jeff went to Toronto. This was my first experience of a kind of an American university campus, and it was really wonderful. I shared a room in the dorms just down the street with a guy called Stan Dehaene, who at the time was actually an undergraduate student in France, and they put us together because we spoke French. And this guy is super famous now. He's like one of the big cognitive scientists in France, like works on consciousness and stuff like that. He's an amazing guy. Okay, so I like to show this picture, which I stole from my friend Léon Botou, who kind of digged it up somehow, which is a picture of the perceptron. So we forget that the perceptron back in the 1950s, which is the root of all of neural nets, if you want, was not actually a program on the computer. It was actually an analog computer, a big machine where each of those little modules here is actually a weight. And the way the weights were implemented, it was a potentiometer with an electric motor on it. And so you would, press the button when the system made an error, and all the motors would go. And so your learning rate was kind of how long you press the button, basically. And that's, spaghetti plate here is the feature extractor. We tend to replace this with spaghetti code now. We can replace this thing now with 3 lines of Python, right? But it wasn't that easy back then. But it kind of created this model of feature extraction followed by classification, which is really the standard model of pattern recognition that people have been using for decades. And so, we all know what supervised learning is, and I'm only talking about it because later I'm going to talk about why this is limited. So supervised learning, as we all know, we have samples from, say, cars and airplanes, and we feed that to a machine that has lots of tunable parameters on it. This is actually an analog synthesizer. We want to turn the red light when we saw a car, the green light when we show an airplane, and we show an airplane, the green light doesn't turn on. We tweak the knob so that the brightness of the green light increases, and we can do this by evaluating the gradients of the cost function difference between what we want and what we get with respect to all the knobs. And the magic of it is that it works even if after training we show it examples it's never seen before. That's the generalization ability. So, ooh, I see what's happening. So one thing that deep learning has brought to the table is the fact that we now have replaced this model of handcrafted feature extractor followed by classifier by the deep learning model, really, which is kind of a cascade, a hierarchical cascade of modules, all of which are trainable end to end, and we can train them with backprop. And of course, the first question you have to ask is what do you put in those boxes? The standard model of neural nets, of course, is those boxes are composed of very simple modules that are essentially linear transformations, multiplication of a vector by a matrix, at least conceptually, followed by a pointwise nonlinearity. Very often nowadays in modern versions of neural nets, it's just a half-wave rectification, so what we call a ReLU. So this kind of succession of linear operation interspersed with pointwise nonlinearities, and then you stack multiple layers of this, it basically has the power to represent a lot of different useful functions. So we all know what backprop does. It basically is a kind of a backward procedure that computes the gradients of whatever cost function we want to optimize with respect to all the internal parameters in the system, which are basically the coefficients in those matrices. And we can do this using a very kind of simple practical application of a chain rule. It's kind of amazing to me that it's an idea that's completely obvious a posteriori, but it took until around the mid-80s for people to realize you could use this for machine learning in an efficient way. The story that Jeff Hinton tells me, so of course the idea of backpropagating gradient to compute things by gradient descent goes back to the kind of control theorists in the 1960s that there's a method called the adjoint method to compute trajectories of rockets and stuff like that. This is what NASA uses to compute trajectory of rockets, and it's basically backprop. It's not used for learning, it's used for control. And the story that Jeff told me is that back in the early 80s, Dave Romenhart had the idea of using just backprop and gradient descent, and he implemented it on his computer using Lisp or whatever, and it didn't work. So he talked to Jeff, and Jeff told him, oh, there's no chance it's going to work, it's going to get trapped in local minima. And it probably didn't work because he had a bug in his program or something like that. And so Jeff later was working with Boltzmann machines with Terry Sanofsky here at CMU, and also working on the Lisp machine. At the time, this was the idea of MATLAB or Python. And he realized local minima was not a problem, and so he re-implemented backprop and actually made it work. And went back to Dave and said, you probably had a bug in your program. And so that's kind of the local story of backprop. I came up with kind of a similar algorithm about the same time, around 83 or so, which I published in French, and that kind of, Jeff was good enough at French to actually read it. But so, of course, one of the things that we've been that people have been using very successfully in recent years, and also all the way back to the late 80s, is convolutional nets. And convolutional nets is nothing more than a particular way of specializing the linear operators and the nonlinear operators that we use in those networks. And so I'm sure many of you are familiar with this. A convolutional net is basically a neural net in which the operations performed by each layer is a discrete convolution. So you take an image, you have a pattern of coefficients, you compute the dot product between the coefficients and the neighborhood. That gives you a value that you pass through the nonlinearity, and you take this neighborhood and you kind of swipe it over, and you record all the values. That gives you a feature map. So each of those feature maps is the result of applying a different filter to the input. And of course, the filter coefficients are going to be learned by backprop. There's the pooling operation, which kind of aggregates the outputs from the filters in an area and creates a little bit of distortion invariance. And this architecture is very much inspired by neuroscience. It's not inspired very precisely by neuroscience, but by kind of general idea about how the visual cortex is organized. So this is inspired by very classic work, Nobel Prize winning classic work in neuroscience by Huber and Wiesel. From the 60s, and there was this gentleman, Kuniko Fukushima, in the 80s, who built a model called the neocognitron that was, basically very much this kind of architecture, but he didn't have the backprop algorithm to train it, so he was kind of more interested in sort of modeling the brain. But they had this idea of kind of simple cells and complex cells, the pooling and the convolution and pooling. So the advantage of this is that, of course, the system can learn hierarchical representations of images in a fashion that is increasingly abstract and invariant as you go up the layers. And that idea of kind of hierarchical abstraction is really what makes deep learning so interesting. So over recent years, of course, Jeff, again, and his students, and various other people in my lab, and Yoshua Benjo's, and Druing, and a bunch of other people have, of course, scaled up those convnets and various other neural nets and trained them on very large data sets, like the ImageNet data set that has, 1 million samples or so. And really what made this work is not just the idea of ReLU. There's a few new ideas, like using ReLUs instead of sigmoid functions, dropout regularization, which I'm not going to go into, and various other tricks of this type. But really, what made this work on a grand scale was implementation of those on GPUs, so we could train very large networks relatively quickly, and the availability of very large labeled data sets of images, speech, etc. So rather than sort of revolutionary new ideas, it's really kind of computation and data that caused the kind of recent revolution. So we end up with systems that are kind of, I remember at the summer school, we were, back in '86, this was the first time that kind of we realized that a neural net was really kind of a statistical estimation system. And we all told ourselves, it's kind of crazy to have gigantic neural nets when we have few data sets, few data samples, because we're going to run into overfitting. So overfitting was kind of a big word at the time. And people started thinking about regularization and pruning and things like that. And it turns out all of those ideas that a network should be relatively small if you don't have a lot of data were essentially wrong. What we do now is we make those networks bigger and bigger, and they just work better. And even without additional data, which is a big mystery, really, because there is kind of a threshold of data that you need to get them to kind of just work. And then above this threshold, you just make them big and big and big, and they work better and better. So it's kind of a theoretical mystery a little bit. There's some sort of self-regularization going on, and a bunch of applied mathematicians are getting interested in this, so it's good. So of course, why we need this hierarchical representation is the fact that the world is compositional in the sense that pixels assemble to form edges, edges assemble to form motifs, and motifs assemble to form parts of objects assemble to form objects, etc. There is a very nice little phrase from Jason Eisner from Johns Hopkins, which I very much like. He says, the reason why it's good that the world is compositional is because it makes it understandable. And what he says is that the world is compositional, or there is a God. So this idea of hierarchy is particularly as I said, sort of somewhat inspired by biology in the sense that the visual system itself is hierarchical with a bunch of layers. And for everyday recognition, it looks like it's essentially a feed-forward process in the mammalian brain for recognizing objects. Of course, not all of human vision is feed-forward, but sort of simple object recognition seems to be mostly feed-forward. So what we've seen over the last few years is an inflation of the number of layers in the sense that instead of like the old style convolutional net had 7 layers or so, the ones that work really well in 2013 or so had 15 to 20 layers. And now, so VGG, for example, that was kind of one of the record holders in 2013 has 20 layers. And then we saw the Google LeNet. This is kind of a play on word on the LeNet. I didn't give that name, by the way. This was my boss at Bell Labs who picked the name. Which had this inception architecture that has a large number of layers. And more recently, ResNet from Kai-Ming He, who at the time was at Microsoft Research Asia, who is now at Facebook, came up with this ResNet architecture where each pair of layers is essentially the identity function, and what the layers are doing is computing a deviation from the identity function. And that turns out to make the network very robust and kind of allow it to sort of stack many layers without paying the price in terms of optimization. And the amazing thing is that it works really well. So we realized pretty early on that we could use convolutional nets for all kinds of stuff, not just recognizing single objects like characters, but also recognizing multiple objects. Like we could do simultaneous segmentation and recognition of multiple objects, as is shown here, with a very simple kind of post-processing that extracts the most likely interpretation. We could do face detection. There's some early work on this in the early 90s. And more recently, we could do things like pose estimation, all kinds of stuff. More relevant to the kind of self-driving car crazy people around here, you could do things like train a robot to using a convolutional net. You can train a convolutional net to basically label every pixel in an image as to whether it's traversable or not. So this is a DARPA project called LAGGER, Learning Applied to Ground Robots. The robots for that project were actually built here at NREC, and what the system does is that it trains itself using label produced by stereo vision systems, which produces label to train a convolutional net, and the convolutional net is monocular, so we can label pixels very far away. And the system trains on the fly while it's driving around. So this is this robot, again, built at NREC. This is Raya Hetzel. She was actually a postdoc with Martial and Drew Bagnall for a bit. Now she leads the robotics research group at DeepMind. And this is Pierre Samanet. He's now at Google. This was many years ago, 8 years ago now. Yeah, they're making the life of this robot a little impossible, and they don't hesitate to jump in front of it. I mean, this robot, like, can break your leg. It weighs 100 kilos or so. But they're pretty confident it's not going to do that because they wrote the code. And they trained it. Okay, here is another example, more recent, where we kind of work on using a similar architecture. We train a convolutional net to do semantic segmentation. So with a sliding window approach, you can apply the convolutional net at every window on the image and basically train it to classify the central pixel in that window with the category of the object it belongs to. So you have the road, the buildings, the windows, the person, the trees, the sky, and then occasionally it completely fails. You get the beige areas here are classified as desert or sand or beach. This is the middle of Manhattan, so there's no beach I'm aware of. This is actually in the middle of the NYU campus, Washington Square Park. So we thought this was really cool, and eventually we implemented a version of this on FPGA that could run at 20 frames per second, and I think that had to have an impact on people working on self-driving cars who kind of realized they could use something like this to build self-driving cars. So you apply a convolutional net to the image, you train it to do semantic segmentation where it labels all the pixels that are traversable and perhaps the pixels that are obstacles, and that kind of is a good starting point for driving. So this is the Mobileye system. That's a video from them. This is what was built into the Teslas until recently, until they divorced, but it's pretty effective. And more recently, NVIDIA got interested in the similar problem, and they have several teams working on self-driving cars as well. And of course, at CMU, this pioneering work by Dean Permelo and others, hey Dean, on using neural nets to drive cars around. So in fact, some of the work that's going on at NVIDIA currently in New Jersey by some of my friends is very similar to your system, where you show an image to the system and you kind of train it to emulate the steering angle of a human driver. And after a couple thousand hours of training, running on a tiny machine like this one, it can basically drive the car. I drove in that car. Well, I did not drive in that car, but I was in the car. The car was driving. It works pretty well. So more recent work on computer vision is some work that was done at Facebook, which I was not directly involved in, building on some original work by Pinheiro and Colbert, who are Colbert is at Facebook, Pierre Dollard also is at Facebook. And this is not just recognizing objects, but also producing the outline of an object simultaneously. So it's just a convolutional net, and it has a category called output, but also a mask that is supposed to represent the object that's being currently recognized. And you can apply this thing with a sliding window at multiple scale over an image, and it will produce object categories as well as masks. These are the kind of results that the system produces, where it outlines the phones and the person, the laptop, the people hidden behind chicken wire, people that you only see the heads of. And look at this guy. It's a person. It's a frisbee. You can pick out broccoli out of Chinese dishes. Which is great because I don't like broccolis. And you can also count sheeps. So this, there's nothing that looks more like a sheep than another sheep, particularly if it's in front of it. And this kind of problem would have been very difficult to solve. You would have asked a computer vision researcher just a few years ago, how long will it take for us to be able to do this? Not clear what the answer would have been. Particularly since the system does not just recognize sheep, it can recognize just about, like 200 categories or something like this. This sheep here is broken in half, so not very lucky. Okay, something else I want to mention is that if we want on the way, okay, so we have a good handle on perception, but perception is not all of AI. So if we want to make progress in AI, what we need to be able to do is get machines to reason, remember things, make inference, turn facts and text into operational knowledge. And there is kind of an area now that's becoming quite popular called, I guess, differentiable computation, but more specifically something called memory augmented networks. So these are essentially recurrent neural nets that are augmented by a memory in such a way that this memory is itself a differentiable circuit that can be used as part of the learning and can be trained. So there's several models of this type. Of course, you could think of LSTM, the long short-term memory, from Ohrheiter and Schmidhuber from the late 90s as kind of a simple form of this. More recently, there is the memory network and the end-to-end memory network of Weston et al. At Facebook. The stack-augmented RNN of Armand Joulin and Thomas Mikolov, also at Facebook, and the neural Turing machine at DeepMind, as well as the more recent differentiable neural computer from DeepMind as well. So what is a differentiable memory? It's something like this. It's really a RAM circuit. For those of you who are kind of have an electrical engineering background, you'll probably recognize the circuit. So the input is, you can think of it as an address. It's a vector, really, a continuous vector. And the vector is being compared with keys, a bunch of keys, using a dot product. So out of this comes a score, which is a number between -1 and +1 if the vectors are normalized. You plug this into a softmax function, which is exponential normalized by the sum. And what you get is a bunch of coefficients between 0 and 1 that sum to 1. And what you compute is a weighted sum of those value vectors weighted by those coefficients. So if this vector exactly matches that vector and is orthogonal to all other vectors, then this output would be 1, the other ones would be small, and then you will get at the output just this vector here. So that's would be operating like a RAM if you want. But it's all soft and differentiable. So how can you use this? So you can use this system, for example, to build a machine that answers questions. What you do is you take a question formulated as a piece of text. So first of all, you have a machine read a piece of text, and you store each sentence in the text in the memory in the form of a vector. So you can take a sentence and code it into a vector using a function of some kind, like a bag of word kind of lookup table kind of thing. And you can learn this. You don't have to dream it up in advance. But anyway, so you have the machine read the text and then store the text in the memory. And then what you do is you plug a question in the form of the vector that represents this question. And this runs through a neural net that will generate an address for the memory, get the output back from the memory, add it up to its current state, and then combine it with some function, again, another iteration in the recurrent net, and then repeat this a few times. And then at the output, you tell it what the correct answer to the question is, and you train this with backprop. So the backpropagation is going to train the recurrent net to produce the correct address that will produce the correct answer with the fact that is relevant for answering the question. And the amazing thing is that it works. So you can do things like have a machine read a 15-sentence version of Lord of the Rings which is basically all you need to know about Lord of the Rings. And sorry, I offended like 2/3 of the audience right now. I actually like Lord of the Rings, okay? But don't read the last 3 sentences if you haven't. And then you can ask. So these are stored as items in the memory, and then you can ask where is the ring in Mount Doom, where is Bilbo now, Grey Heavens, etc. So that works really well. There is actually slightly more complex types of questions the system can answer. Things like this: Brian is a lion, Julius is a lion, Julius is white, Bernard is green. What color is Brian? So Brian is a lion, and the other lion is white, so probably white. Or so things that require kind of putting together a bunch of different facts. And so there is my colleagues at Facebook, Jason Weston and his colleagues, have come up with sort of 20 different types of questions that they call the baby task or BABI task, B-A-B-I, which are basically different types of questions that we might want to ask question answering systems of this type that include basic deductions and lists and counting and yes no questions, etc. And this memory network works pretty well. It solves 19 out of the 20 pretty much with no problem. But this 19, the 20th one is kind of annoying that it can be solved. So more recently, this is a paper that was just submitted to ECLIR. Is the entity recurrent neural net, which is a form of memory network that's very different from the previous one I showed you. And the role of this network is to maintain a current estimate of the state of the world. So the system reads a sentence once at a time and is supposed to update its internal state so that it maintains a current state of the world. And that allows it to kind of do things like keep track of how many people are in a room and things like this without being told what a room is even. And so what the system is composed of is a bunch of units, each of which is supposed to represent an entity, but really it's a distributed representation. So all of those kind of store vectors, and they are kind of recurrent nets if you want. And those recurrent nets are being updated by the input, which is broadcast to all of those memory cells. So in an ideal situation, each memory cell represents an entity in the text. Let's say a room with its content, or a person with its location and the objects the person holds, etc., etc. And then those things are being updated every time kind of an event occurs, or a text is being fed that describes an event. And this is trained end-to-end to answer questions, right? So there is a story being told, and then at the end a question, and then the correct answer, and then the thing kind of backpropagates. And this one solves all 20 of the BABI tasks. Okay, so let me switch gear and talk about obstacles to AI and really what the future of AI. I think the next steps that we should take to make progress in AI. So my picture of an AI system is something that can have perception, of course, that needs a predictive model. I come back to what I mean by this. Has memory, kind of like the memory network, and has reasoning and planning. And you'd like all of those things to be sort of self-differentiable parameterized functions, so you can use all kinds of learning algorithms, minimize loss functions of various kinds to train this. So why do we want to kind of train AI systems? I think it's because the big prize in AI that a lot of people have been working on in classical AI since the beginning is the fact that is to attack the problem that machines don't have common sense. So we kind of all have some intuitive notion of what common sense is, but machines really don't have it, that's for sure. They have kind of a very shallow understanding of text, no knowledge really of the physical constraints of the world. And so that's crystallized in what's called the Winograd schema, which is a type of sentence that has a pronoun in it. And what the pronoun refers to is ambiguous depending on how you build a sentence. So if I say the trophy doesn't fit in the suitcase because it's too large, you know that the it refers to the trophy. If I say the trophy doesn't fit in the suitcase because it's too small, you know that now that the it refers to the suitcase. And there are lots of ambiguous sentences like this you can come up with whose resolution depends on your knowledge of how the world works, kind of the constraints of the physical world. If I say Tom picked up his bag and left the room, I don't see Tom Mitchell here, but I'm sure he's. With just those few words, you can sort of infer, you can fill in a lot of blanks that are not mentioned in this text. You can imagine a lot of the details of that situation. Tom, first of all, is in a room. He's probably going to stand up, extend his arm, pick up his bag, close his hand around his bag, walk. He's probably not going to fly. He's probably not going to dematerialize like this guy. He's probably going to walk towards the door and open it. He's probably not going to walk right through the wall. Once he's gone out of the room, he's not there anymore. You can't be in two places at the same time. So all of those basic facts about the world, we learn when we're babies. But we learn them by just observing the world. Nobody kind of teaches us all those things. We learn that the world is three-dimensional. How do we learn that the world is three-dimensional? We probably do it because we need to be able to predict what the world is going to look like when we move our head 20 centimeters to the left. And the best explanation for how our view changes is depth. And so we come up with a representation of depth. But we're not born with this. We're not born with the fact that when an object is hidden behind another one, it's still there. The notion of object permanence. Babies learn this in the first few months of life. We're not born with the fact that when an object is not supported, it's going to fall. Babies learn this between the age of 6 months and 8 months. This is actually very well measured. So all of those basic facts about the world that we take for granted, there's millions and millions and millions of them. We learn them unsupervised. So I think the key to common sense and the key to making progress in AI system is learning how the world works by observation and perhaps by action as well. But how do we get machines to do this? So that took me to this analogy, and I apologize in advance to everybody who works on reinforcement learning here. I do too, so some of my best friends are reinforcement learners. If you count the amount of information that is provided by the environment to a learning machine at every trial, however you define a trial, the amount of information given in the context of reinforcement learning is basically a few bits per sample. It's basically a scalar value for each trial. In supervised learning, it's a bit more. It's a vector of desired outputs, essentially, or a category. Okay, so it's a few more bits. For unsupervised learning, which consists in really kind of predicting the future, filling in the blanks, etc., there's a huge amount of information that the environment gives you that you can ask the machine to predict. And there is no way you can train a very complex machine with billions of parameters with just this. It will require a ridiculously large amount of samples. So in fact, you can notice that all the success of reinforcement learning are in games. Why is that? It's because games you can simulate on the computer very quickly, and you can train the machine with millions and millions of examples. But it completely fails on its face when you train it in the real world. You cannot do model-free reinforcement learning in the real world. And the reason is simple, is because you can't run the real world faster than real time. And that kind of sucks. So that led me to this analogy that if you just count in terms of amount of information you provide to the machine, if you imagine that intelligence is a cake, the génoise, the bulk of the cake is unsupervised learning, the icing on the cake is supervised learning, and the cherry on the cake is reinforcement learning. And again, you want a cherry on top of your cake, but it's not going to solve the problem by itself. You need unsupervised learning for reinforcement learning to work. It kind of doesn't make sense to have just a cherry without the cake underneath, right? Okay, so let's talk a little bit more specifically. What's the architecture of an intelligent system? And this is really kind of a diagram that's very much simplified and inspired by what neuroscientists tell us, but it's kind of an old type of diagram. So an intelligent agent really has two components. It has the agent itself, if you want, and it has something that agent doesn't control, which is sort of an objective function of some kind, which basically determines what the agent lives for. Okay, so this module reads the state of the agent and tells the agent you're happy or you're not happy. And it can tell it you're happy in different ways, right? So depending on the state, it can tell it how it's not happy. It can be hungry, it can be scared, it can be thirsty, etc. The agent produces actions that act on the world, and the world responds by producing percepts or observations that the agent uses to estimate the state of the world. And you have this loop, and the goal of the agent is to put the world in such a state that it's going to make itself happy and satisfy its objective function. So this is not like reinforcement learning where the reward comes from the world. Here the reward is an intrinsic function that reads the state of the agent. And this is how our brains are built. there is kind of an immutable piece of goo at the base of our brain that basically computes whether we're happy or not. It's not immutable. You can take drugs to affect it, but it generally doesn't end very well. Now you can ask the question, what does the agent have to contain to act intelligently? And one thing it can try to do, of course, is being reactive. So basically try a lot of different actions until the objective function is minimized, if it's a cost, if it's unhappiness, for example. So you try lots of things, and it keeps trying things until the cost is minimized. But that's sort of very inefficient because, again, the world runs in real time, and it doesn't run faster than that. And so, and furthermore, some of the things you might try might actually kill you. So this is not a good way to learn. It's very slow. It's very inefficient. So to make the learning more efficient, you can use what's called model-based reinforcement learning, which consists in essentially building the agent in such a way that it has a simulator of the world inside of itself. So it has a way of simulating the world, a world model, a world simulator, or a forward model, as we call it sometimes. It has an actor that generates action proposals that act on the world. And this actor can actually read the internal state of the simulated world. And then it has a critic, and what this critic does is it predicts the ultimate value of this objective function. So it tries to kind of predict what's going to be the long-term effect of taking those actions by kind of seeing the result on the world. So at the beginning of deciding what actions to take, the percept comes from the world and initializes the world simulator in a particular state. So the role of perception is to really get an estimate of the state of the world. And then the actor generates a sequence of action proposals and see which one works, and you can kind of simulate this multiple times. This is called a rollout. This is a technique that was used in various contexts in reinforcement learning in the old days. It's used currently also by a few people who do model-based RL, like Sergey Levin at Berkeley, etc. So if your world simulator is itself a neural net and is differentiable and is trainable and somehow simulate the world appropriately, then you can use gradient descent to figure out what sequence of action will make you reach a particular goal. You don't have to do discrete optimization or exploration or anything like this, combinatorial optimization. You can use gradient descent. And this whole network here looks like essentially a recurrent net that has been unfolded that you can backpropagate gradient through so as to optimize the ultimate value of the cost function here, while maintaining the fact that the world simulator actually simulates the worlds, and while maintaining the fact that the critic actually predicts the ultimate value of the cost function. So that's kind of the basic architecture, perhaps, of an intelligent system. But the main problem in there is not really how to figure out the sequence of action if we have a good world model. It's not really how to learn the critic or the actor. It's really how to train the world simulator. Why is it hard to train a world simulator? It's because the world is very unpredictable. So here is a very simple experiment that my colleagues Adam Lehrer, Sam Gross, and Rob Fergus at Facebook did, which is to use a game engine, which is the Unreal engine, a game engine that we hooked up to Torch, which is our deep learning framework. And this is open source, so you can play with that if you want. It's called UE Torch. And so it allows you to kind of run physical simulations in a game engine and then get the outputs and the mask of the objects and things, depth maps and stuff like that, and use that to train a network. So what they did was train a network to predict what's going to happen to a tower of blocks. And so here is kind of an example of a tower of a few blocks, and this is what actually happens in the simulator. And this is what the system predicts is going to happen. And you get kind of fuzzy predictions because you can't have an exact fix on the position of everything. But it works pretty well. It even works with real towers that are not simulated by Unreal, including tall towers. But it gets fuzzier and fuzzier as the towers get taller because there's more uncertainty. So how do we deal with uncertainty? That's the topic of unsupervised learning, really. And so what is unsupervised learning? So I have a very personal definition of unsupervised learning. And it's one by which a system is supposed to capture the dependencies between various variables that are either observed or not observed, and learn a contrast function that tells you whether a point in that space is near the manifold of data or far away from it. Okay, so here is a bunch of data points in a two-dimensional space, and you can sort of identify where those points lie. And what you'd like is a contrast function that tells you when you give a y vector that's kind of near this manifold, it tells you 0. And when you're far away, it gives you a positive number, maybe proportional to the distance. Some function kind of like this, okay, that kind of increases value as you move away from the manifold of data. And what you'd like is to be able to learn that function, that contrast function, so that it takes low values on the data points and higher values everywhere else. So one way to do this is you build a machine that takes an input vector y, produces a single scalar, which is the height of this function at this particular point y, and you show it a data point, a real data point, and you tweak its parameters so that its output goes down, okay? So that you give low energy to those blue points. And then you show another point outside. How you generate this, I leave it up empty for now. And you're going to push that up. So you're going to generate one of those green points, push the energy up of that, so that the output of this learning machine is a positive number larger than 0. So these are kind of implausible points, and these are kind of plausible points. And there are kind of 7 or 8 different ways to do this, which I'm not going to go through. I used to show this slide because there's a lot of techniques here that you can kind of reformulate a lot of classical unsupervised learning algorithms in terms of learning a contrast function that you want to take low values on the data and higher values everywhere else. So things like Boltzmann machines, contrastive divergence, score matching, sparse autoencoders, denoising autoencoders, maximum likelihood with Markov chain Monte Carlo methods for variational approximation. I mean, there's all kinds of methods for doing this. And what you want in the end is some contrast function. So if you use PCA, for example, if your points are sampled along the spiral and you use PCA to learn them so that you reconstruct points that are maximally close to this spiral, you get this kind of energy function where PCA gives the principal axis of this data and increases everywhere else. That's not a very good model of this. With k-means, you get better results here where you get essentially a prototype. You get prototypes along this surface, and you get low energy along the surface, higher energy everywhere else with a quadratically increasing error function. It works in low dimension, doesn't work so well in high dimension. This is what you get with sparse coding. You kind of approximate the surface with sort of a union of planes. But the best idea ever, which is misspelled, is adversarial training. So adversarial training is a really, really, really cool idea. Let me repeat this. It's like the coolest idea in machine learning in the last 20 years. No, really, I'm really not kidding. I'm a big fan of this idea, and it's not my idea. It's an idea from Ian Goodfellow, who was at the time a student with Yoshua Bengio at University of Montreal when he came up with this. This was a paper in NIPS 2014. And I think it's the coolest thing ever, okay? So let me kind of set the stage for what it is. Let's say we want to do video prediction. So basically we want to learn a forward model of the world, right? We want to be able to tell a machine, here is what just happened, tell me what's going to happen next, tell me what the world is going to be like half a second from now. Okay, so a very simple example is the machine observes someone putting a pen on the table and lifting the finger, and then you ask the machine what's going to happen. And so this is kind of a neural net, and this neural net takes the past video frames. It takes a source of random numbers, perhaps representing the hidden state of the world or something like that, and it produces a prediction, which is, the pen is going to fall to the left and to the back. Let's say it's that point in the space of outputs. But in fact, we run the video, and the world disagrees. The world actually produces this. So what actually happens in the video is that the pen falls to the back and to the right, which is this point. So what you'd like is you'd like to be able to tell the machine, okay, you got it wrong, but you didn't get it conceptually wrong. You kind of got it on the right sort of set of plausible outputs, right? And so I don't want to punish you for putting a point on the set of plausible outputs, even if it's not the point that actually occurred in the future. And so the next question is, how do you how do you characterize this surface of possible futures and tell the system that it doesn't need to be punished for not making the right prediction. So first of all, if you used a traditional supervised learning technique like least square, the best thing the system could do here is basically predict the average of all the points on this ribbon here, which would be kind of somewhere here. And this would look like a transparent superposition of the pen in all possible orientations around. And it's not a good prediction. It's not on the ribbon. It's outside of it. The average of points on the ribbon is outside the ribbon. Okay, so that's why classical supervised learning that trains to produce a particular point is not sufficient for this. So now the next problem is, how do you characterize this ribbon? Who tells you what this ribbon is? And so the cool thing about adversarial training is that you train a second neural net to learn what this ribbon looks like. Okay, so you train two neural nets, and it's called adversarial because they train against each other. So here's how it works. You have the generator. It takes the past. It takes the source of random numbers. It produces a prediction, which is one of those green points initially. And then you have a discriminator, and this is your trainable objective, your trainable energy function, right? So it's this surface. It's going to train itself to compute the surface that will give you low values on the data point, on the real data point, and higher values everywhere else. Okay? So the way you train this is you take a sample from the data set, you feed it to the system, it's one of those blue points, and you adapt the parameters of the discriminator so as to minimize its output, okay, give it low energy. And then you run through the generator, have it generate a point, it's going to be one of those green points. You run it through the discriminator, and the discriminator is going to train itself to increase its output, make it large so that it learns the surface. But then the trick is the generator is going to train itself to generate y's that are closer and closer to the manifold of data. In other words, y's that produce lower and lower values on the output of the discriminator. And so next time around, the generator will have become a little better and perhaps will produce those green points. And next time around, it's going to be a little better and produce those green points and do a good job. And in the end, there's an equilibrium, which is kind of like a Nash equilibrium, where the discriminator basically can't tell the difference between the real data points and the ones that are generated by the generator, and the generator hopefully generate points that are really on the conceptual manifold. So this is called, this formulation of generative adversarial network is called energy-based GANs, and it's been on archive for a couple of months. It's a submission to iClear by Jake Zhao, who is a PhD student with me, Michael Mathieu, and myself. So GANs have been used for generating images from random numbers. This is a very famous work called DCGAN. This means Deep Convolutional Generative Adversarial Network by Radford, Metz, and Chintala. Chintala is at Facebook in New York, where they train it on images of bedrooms, and then you put a bunch of random numbers to the convolutional net or reverse convolutional net, and it produces bedroom images. And these are fake bedroom images. And they look great. They're pretty low res, but they look nice. You can interpolate between manga characters. You can do arithmetics on faces. So you can take the vector that will generate the face of a man with glasses minus the vector that will generate the image of a man without glasses, then add the vector of a woman without glasses, and then when you regenerate the image, you get a woman with glasses. That's kind of cool. So in those space of random numbers that feed into the network that parameterize the surface, you get some sort of flat property that allows you to do this algebra kind of thing, analogy type things. This is, to some extent, the holy grail of generative models that people have been looking for decades, which is, give me a way to parameterize a very, very complex surface in a high-dimensional space. That actually does it. It's the first time I see anything that does it to that degree. So the energy-based GAN has another trick, which is the discriminator itself is some sort of energy model based on an autoencoder. I'm not going to go into the details of it. But the cool thing about this is that it can generate images at relatively high resolution that look realistic. So if you're in the back, you might think that those images, so this has been trained on ImageNet, and those images kind of sort of look nice. They kind of have some object in the center. You can't really tell what they are. And if you're on the front, you're saying like, what the hell is this? Like, it's like none of those actually are objects of any kind, right? There's some sort of like sea and sky and something that looks kind of like a airplane or a sailboat or train, a TGV or some kind. So you can't really make it up. If you train on dogs, you get soft dogs. This is like, you would think that this thing has been trained on like Salvador Dali paintings or something, but and so it gets the idea of a dog, but like not the kind of global structure really. And those are 256 by 256 images. This is the first time that anyone has trained a GAN on high-resolution images like this successfully. So here's another example for video prediction. This is actually a paper from last year at iClear with Michael Mathieu, the same guy. Camille Coupry, she's a research scientist at Facebook AI Research in Paris. We have a lab in Paris. For those of you who have become undesirable in this country, you can always go to Paris. So if you train this convolutional net to predict video in a supervised manner using least square, the prediction you get are things like this, very blurry. So the first 4 frames in this snippet are observed, and the last 2 frames are predicted. And you get blurry predictions because, again, the system predicts an average of all the possible features that can happen. But if you train adversarially, you get this. So this is least square, and this is adversarial training with a little bit of regularization. And it does a much better job at predicting. The first 4 frames are observed, the last 2 frames are predicted. Same for all of those snippets. The bow of the cello kind of continues. This string kind of continues. The cameras keep moving, etc. These are other examples where the system has been trained on videos of it's like a camera that kind of pans around in apartments in New York, essentially. And again, the first frames, the blue frames are observed, and the red frames are predicted. So this is 5-frame prediction. And what's cool is the thing has to basically invent what the apartment looks like in places it hasn't seen, right? This is a test set. So look at this bookcase, for example. It's got to dream up the continuation of the bookcase. Same here. It's a library. So it's kind of cool. It's going to capture something about the world, and it doesn't produce blurry prediction. If you ask it to predict at 50 frames, though, things get bad really quickly. You kind of get washed out predictions and etc. So it's not like the problem is solved at all. What we probably need to do is have some sort of hierarchical way of doing those predictions. Okay, I'm going to thank you for your attention, and I'm going to stop here and take questions. Thank you very much.
Dean.
Hi, Yann.
Hey, Dean.
Great stuff, but the elephant in the room. Facebook's getting roundly criticized for the problems associated with the election, particularly the echo chambers and the fake news that has permeated Facebook, and some are saying influenced the election. Not the image stuff, but there's definitely interesting natural language processing. Those 2 problems seem amenable to machine learning and natural language processing. I'm wondering, what is Facebook and your team in particular doing to address those 2 big problems?
So, okay. So there's a lot of things on this topic which I'm not the right person to answer, and basically I'm not even authorized to talk about it. But what I'm going to say is that there's 2 issues there. One issue is a technological issue. Can we build systems that detect if news is fake or something like this? And I think, frankly, the problem is not completely solvable, but there's probably things that can be done automatically using machine learning techniques, deep learning, natural language understanding methods. Some of that has already been done in prototypes. Then there is a wider question, which is that it's a question of policy and product design, and that's completely outside of my territory. I'm a researcher, and so you'll have to ask that question to someone else. But what I can tell you is that there is a lot of thinking about this question at Facebook right now, and so you'll probably hear about this soon.
Yeah, you.
Thank you. I really appreciated your talk. Kind of going off of that, I wanted to come back to the common sense knowledge that you were talking about. And I wondered if you could talk a little bit about how common sense knowledge is culturally and historically situated. So for instance, like we can expect to carry a bag this way because we live in the West, but maybe you could carry it this way if you lived in a different situation. If I think about the rooms that were automatically generated, they looked like wealthy rooms that people might live in. So I think that kind of particularly relates to questions of racial representation in AI.
Okay, well, that's a different kind of worm, if you want. But okay, certainly the systems you train on a particular type of data will reflect all the biases that are in the data. And so, I don't know, some of you are maybe perhaps aware of an initiative called the Partnership for AI, which is an initiative that was started by myself at Facebook, Demis Hassibis and Mustafa Suleyman at DeepMind, Eric Horvitz at Microsoft, Rob Furbrick at Amazon, and Francesca Rossi at IBM. And we created a nonprofit organization to really kind of discuss in the open those questions of how do you build machine learning systems that are not like ridiculously racially biased. As what you say, there is a paper that just appeared on Archive yesterday, which I'll let you dig if you want, where the people there claim that they can just, with a picture of the person, determine if this person is a criminal or not. This is like the epitome of unethical machine learning research. And they're using a convolutional net, obviously. So people do stupid things sometimes, and I think it's good for this community to really reflect about how to do this ethically, and perhaps give guidelines on what to do and what not to do. And this is, in my opinion, something that really is inappropriate.
Over there. Yeah.
First of all, thank you for the talk. And my question would be, could we go a little bit more in detail to the difference of these neural networks versus like already explored methods like restricted Boltzmann machines and all encoders?
Okay, so the question is about the difference between these type of neural nets, trained with backprop essentially, compared with restricted Boltzmann machines or Boltzmann machines and various other types. Yeah, I mean, there is like the Pope of Boltzmann machines was, is Jeff Hinton, and the top bishop is Russ Salakudinov, right? So, who is here. Well, so yeah, he's here. You can ask him. He used to work on Boltzmann machines. He's now mostly working on this kind of stuff. So there's a reason for this. So Boltzmann machines are part of the set of models that are trained unsupervised. They're supposed to kind of learn those density models of some kind. And to some extent they do. There's like a few demonstrations that are very impressive of Boltzmann machines kind of generating, motions of motion capture data and digits and stuff like that. The problem is that it doesn't seem to scale very well. So the particular way those contrastive samples are generated, which is using contrastive divergence, you start from a data point and then you move down with some randomness in the energy surface, and then you get this point and you push it up, right? And it doesn't seem to scale very well in high dimension. So I think that limits the applicability of Boltzmann machines. I think adversarial training is actually a much better way of doing this.
Okay, T-shirt in the front, then on the left. So you first, and then you.
Okay. So when you were talking about infant cognitive development as an example to unsupervised learning, you mentioned that certain skills appear at certain time frames, like object permanence. We know that it's between 6 and 8 months. I don't know, hand-eye coordination after 3 months, etc. Why do you think, if it's truly unsupervised, why do you think it's so deterministic?
Okay, so yeah, the question is for those in the back, why is it that the stages at which a child develops and learns certain skills is relatively deterministic? If it's completely unsupervised, why is it so deterministic? So first of all, it's not clear it's entirely deterministic. So this idea that babies go through stages comes from the famous cognitive neuroscientist Jean Piaget. In fact, it's by reading a book of a debate between Jean Piaget and Noam Chomsky that I came to get interested in AI, because there was an article by Seymour Papert about the perceptron, and I discovered that people had been working on learning machines. Like, I didn't know the concept existed. This was like around 1980, 1979. So this idea of stage development is probably due to kind of how the brain is organized, like the development of the brain, the fact that you kind of learn high-level concepts on top of low-level concepts, and there is sort of a natural order in those concepts. The same way the representations in ConvNet is organized, from edges to motifs to parts of objects to objects, you kind of have the similar kind of things. You can't learn that objects that are not supported fall until you've learned the concept of object, for example. And you can't learn the concept of object until you've learned the concept of an object being in front of another, which gives you parallax. That's how the concept of object comes up. You can't learn the concept of objects until you've seen one move relative to its background. So there's a lot of things like this that need to be built in a particular way, and I think it's more the nature of the data than anything else.
So, very, very quick follow-up. Piaget also has this notion of assimilation versus accommodation. So that's one way of explaining the stage development. Do you think a similar approach would be helpful in scaling up our network architectures?
Right. So it's not clear to me how you scale those up. So the question of how you train this. So for example, one big question I have is how would you train those video prediction systems in such a way that they don't just learn to predict video at 5 frames, but they figure out that in the real world, the world is three-dimensional. There are objects that can move independently. Objects don't move all the same way. The details of textures don't matter. It's more the statistics of it that matters. I mean, there's a lot of things that those systems will have to learn. So, for example, would it be possible to train a system that has been trained with snippets of videos where the camera is translated? Would the system trained to predict what the world is going to look like as the camera is translated naturally come up with the notion of depth? Would they spontaneously represent the notion of depth, right? They should, because that's the best way to explain how the world changes when you translate the camera. But we don't have the techniques for that yet. Like, you train those techniques on this problem and it doesn't quite work. So we're missing something, not clear what.
Okay, go ahead.
So yeah, when you mentioned there's an example about training the system to learn physics. So I was wondering, I did similar experiment, but do you treat it with Newton's first law, or you come into the flow with the great, Greek thinker Aristotle, who thinks everything moves because there's force applied on the motion? Do you learn the deep representation of Newton's law, or you come up with some rudimentary observatory answer to the known fact that you just observed from the system?
Right. So, I mean, there are other people working on kind of learning physics. So the question is, do you feed for a system to kind of learn qualitative physics? Would you feed it with the laws of Newton or Aristotle or whatever root kind of elementary knowledge that it would need? I mean, what I'm interested in really is for the machine to learn spontaneously what qualitative physics is without feeding it any particular law. There are other people working on this kind of problem. Josh Tenenbaum at MIT, for example, is really interested in those questions. Brendan Lake, who was a student with Josh, who's a postdoc at NYU, is working also on this kind of problem. So it's a problem that is starting to kind of gather interest a little bit in the cognitive science community and machine learning as well. What I'd like to see eventually, I think I would have, I could retire essentially if I could train a system to, observe a bunch of physical processes and it will spontaneously come up with Newton's law.
So all these neural nets are pretty much single purpose. Do you think the future for like a multi-purpose net is just training one huge network or stitching together a bunch of smaller systems?
Okay, so the question is whether we'll reach kind of a general, train more general systems. I don't want to talk about artificial general intelligence perhaps, but train more general systems by stitching together specialized systems or by kind of having sort of a grand unified large neural net that trains on all of the above. I prefer the grand unified thing. The reason being that there is very often a lot of transfer that's possible between tasks. So for example, there's a lot of data now that shows that if you train a system to represent the meaning of a sentence by training it to translate the sentence into another language, you do better if you train it to translate it into multiple languages, even though it's a different task. Because there is a lot of shared knowledge between that. Vision systems, most people who train vision systems these days, you pre-train on the largest data set that you have, like say ImageNet, and then you fine-tune it on whatever data that you are interested in. In fact, there is a service inside Facebook that does this, that product groups use, where we have a pre-trained network that's been trained on tons of data to classify all kinds of stuff. But then what's generated is a bunch of feature vectors, and product groups can train their own classifiers for whatever thing they want to recognize. They want to recognize Louis Vuitton bags in pictures. They can train this with just a few examples, and it will work. So transfer learning, I think, is very powerful. But what that tells you is that it's always better if you have the choice between training 2 independent networks for 2 tasks on the same input. You're better off training a single network with 2 different heads. It's true also in speech recognition. There's quite a few papers in speech recognition that show that if you want to do sort of multilingual speech recognition, you can have the bottom of the network be essentially common to all the languages, and then different heads for different languages. And that works much better than just training a completely separate network for each language.
Thank you for the talk, first of all. Very interesting. GANs have been a lot less effective on text than pictures and video. I'd be interested to hear your thoughts on why that discrepancy exists and how we can maybe do research to resolve it. Okay,
so GANs have been less effective on text than on pictures and videos. And the reason is because they are less useful for text. The reason being that what GAN give you is a way to represent uncertainty in a particular way, right? In this kind of energy function, essentially. And so it allows, it's very useful when the output of the system is in a continuous space, because it's very hard to represent sets or level sets of probability distributions or densities in high-dimensional continuous spaces. But in discrete spaces like text, particularly when what you represent is the distribution over the next word, for example, in a language model, you can actually represent the distribution explicitly. It's just a list of numbers that sum to 1 between 0 and 1, right? And so the advantage of GANs in that context is not entirely clear. In fact, there are people, particularly a bunch of folks at DeepMind, who actually are doing the opposite. So they're trying to turn generative models in continuous spaces into something that looks like text models, where you discretize what you do to generate an image is that you view the problem of generating a pixel as a classification with 256 categories, which correspond to the grayscale, the gray levels. And then you take the context of the image on the upper left to kind of generate each pixel sequentially. It seems crazy, but it actually works pretty well. So that's kind of another alternative to represent uncertainty in image space, which is, uses some hypothesis, really, but seems to work. That said, there are attempts. So a naive attempt at using GANs in the text context doesn't work, because you use the generative model to produce a distribution over words, and that distribution is going to be soft, right? It's not going to be 1 and a bunch of zeros. It's going to be kind of the output of a softmax. So it's going to be a bunch of numbers. But then the real data is a bunch of zeros and a 1 in the middle. And so the discriminator can tell right away that it's fake. And so you can't do GANs in kind of explicit representation like that. You have to do it in sort of a latent space, like vector representation of words, for example. And that's been done.
You go.
Hi, thank you for coming out for a great talk. Facebook has a lot of image data from a lot of people, and it already is using, for example, who I or anybody else is seen in images with as a measure of association between people. Is that going to extend to now the things that are in a picture around each person? And what do you think are the ethics of having that kind of database and surveillance technology in a political environment where the new leader really enjoys that increased surveillance and intelligence capabilities for his version of law and order?
So, okay.
No, you should not hold back.
Okay. Again, I'm the wrong person to ask that question because I'm not a policy person, I'm not a product person. But I can tell you one thing. Facebook is used to operate in countries that are considerably less respectful of privacy than the US or Western Europe. So Facebook actually publishes every year how many requests it got from governments in various countries for access to private data from users, and how many of those it accepted to disclose. And it's interesting to see by country what those numbers are. Who do you trust with your data, right? Your cell phone company knows everything about you. I don't know if it's AT&T or not, but there is clear access to that data for the government. that data is protected by companies like Google and Facebook, etc. Very, very, very jealously protected. So, do you trust that to continue? I can't answer that question. Okay, to your first question, Facebook gets a lot of image data. So Facebook users upload somewhere between 1 billion and 1.5 billion photos on Facebook every day. This is just the blue site. This is not, we're not talking about WhatsApp, Instagram, Messenger. It's just Facebook. And every single one of those, within 2 seconds of being uploaded, goes to 3 convolutional nets. One does generate object recognition, extracts features and tags objects. One does face recognition. That one is turned off in Europe. If you move to Europe, after 3 weeks, the face recognition will turn off because you're in Europe. Your model will disappear. And the third one does like content filtering, basically. And so that happens also to some extent for video. So you can imagine the kind of infrastructure that's necessary for this. And that really what powers what makes Facebook useful for people. So when you connect to Facebook every day, Facebook can show you 2,000 or 3,000 pieces of information. And nobody has time for that. So Facebook has to select about 100 or 150 to show you every day. And to do that, the automated system at Facebook have to understand what the content is and have to understand your interest and then select the content that is most likely to interest you while preserving diversity, picking your friends primarily, etc. It's a very kind of complicated thing to tune to kind of really make user engaged. But it's a product issue. It's not really a kind of technology problem.
Oh, there, yes. Go ahead.
Thank you for the talk. I have a question about the AI system architecture. So you have this action critiques. So like reinforcement learning, we also not only have the delayed reward, but also intermediate reward. I just wanted to clarify what are the differences for architecture?
Oh, there is no difference, really. There is no difference with classical reinforcement learning in the sense that the diagram I showed, there's only one difference, which is that in classical reinforcement learning, the reward comes from the environment. Whereas here, the reward is indirect through an observation of the state of the agent by the objective function. So that's what people call intrinsic motivation. The way humans and animals function, the basic drives of our behavior is determined by those kind of low-level objective functions that we're trying to optimize. Yeah, and they're not, it's not a reward from the outside. It's the reward is computed from perception and then kind of interpreted by those systems as to whether we're happy or not. So no, there's no real difference. You can have delayed reward and everything. It's really the same. It's just model-based.
All right. Oh, one last question, okay?
So, where do you look at AI to be 10 years from now and then 20 years from now?
Oh, that's a good question to answer.
Oh, nice. Yeah, wonderful question. Okay, so I'd like to solve this problem. So I think on the path towards making machines more intelligent, I think the next obstacle, the mountain that we know we have to climb, is this problem of unsupervised learning, getting, coming up with techniques that will allow machine to learn forward models, predictive models, or models that fill in the blanks, and either predict the future from the past, predict the past from the present. You get to a scene, you can figure, you can kind of infer what went on. If you're a police inspector, you're pretty good at this. So this sort of basic module that we're missing right now, and how to whether we're going to be able to solve this problem is whether we can deal with training a system to produce high-dimensional outputs with a lot of uncertainty. So I think GAN is the best idea we've had so far. There's a lot of other ideas, of course, like Boltzmann machines and associated techniques. But GAN, I think, is the best idea we've had in a bit. So you would have asked me the question 3 years ago. I'm not sure what I would have answered, but now I said, this is GAN stuff. I'm going to cling to it, try to see how far we can push that, and perhaps that's going to take us past this first mountain. Now, to reach human-level intelligence, the main issue is that we don't see the other mountains behind this big one. And there could be none, there could be another one, or there could be 50 other ones that we have no idea what they are. So, you know, when people ask me the question like when are we going to have like human level general intelligence, I said like no one in their right mind will tell you it's going to be less than 20 years. And if someone tells you it's more than 20 years, what that means is that they have no idea how long it's going to take. Because we are very, very bad at predicting kind of major changes of this type with that length scale. For example, it's been 50 years that fusion power was 25 years away, right? And it keeps being 25 years for the last 50 years. So, so I think it's, you know, there are people who are very optimistic in the domain who think, you know, it's just around the corner. I'm personally very doubtful. I think there's way more problems than we think there are. I think we're going to make significant progress over the next 10 years. Like I hope within 10 years we'll have intelligent virtual assistant that we can hold a dialogue with that can answer basically any question whose answer is somewhere on the web or on Wikipedia or whatever. So here is a good unsolved problem in NLP. Take all of Wikipedia and turn this into an operational knowledge base in such a way that an agent can answer any question whose answer is in Wikipedia. It's an unsolved problem. Until we have that, I don't know how far we can go with intelligent virtual assistants. And so, you know, I think we'll have useful intelligent assistants in 10 years, certainly. 20 years, who knows?
Thank you.
Thank you.